Welcome to episode 7 of the Euler Project, a video series in which we take the problems of the online Euler project and solve them, and then take them to the max. Euler 7 is a simple little problem that asks us to find the 10,001st prime number. Now, it turns out that this problem is not very difficult to solve, especially when you consider all that lovely prime number code we wrote back in episode 3. So let's just fire that code up and ask the question directly. So here's the old Clojure code that we used back in episode 3. This was the slow version. Remember later on we wrote a really fast Java version? Well, this is the slow version. And I used that just to find the 10,000th, there it is, the 10,000th prime out of the first 20,000 integers. And the reason I chose 20,000 here is because back in episode 3, we figured out the density of primes. And out at this level, the density of primes was more than 1 in 20. So I think it was about 1 in every 15. So if we go 20,000 integers out, we're bound to get the 10,000th prime. And of course, the answer is 104,743. And that is, in fact, the right number. So this was not a really challenging problem. So let's make this problem a little more interesting. Let's find the 1 billionth prime number. We choose to go to the gigaprime. We choose to go to the gigaprime. We choose to go to the gigaprime and do many other things, not because they are easy, but because they are hard. Okay, so let's do a little bit of math here. Now we're going to use the sieve of Eratosthenes, right? And that means we're going to need an array of booleans. Now, how many booleans are we going to need to get out to the billionth prime? Now, you may recall from episode 3, we measured the density of primes. Remember when we did that? And we went all the way out to like the 10 millionth prime. And out there, the density of primes was like 1 in every 15 numbers. But we also noticed that the primes get farther and farther apart the further you go. So I'm guessing here, but I'm reckoning that probably the density out at the billionth prime is going to be like something like 1 in every 25 or 1 in 30 or something, which means, well, I mean, it's 1 byte per boolean, so that means like 30 gigabytes. 30 gigabytes? 30 gigabytes! Great Scott! How could I have been so careless? 30 gigabytes? Edgar, Alan, where am I going to get that kind of memory? Okay, I couldn't resist, but that was maybe a little overdramatic because, modern computers all nowadays have more than 30 gigabytes of RAM inside them. However, we do have a different problem. Java arrays are subscripted by ints, and ints are just 32 bits with a sign bit on the end, which means that the highest subscript in a Java array is something on the order of 2.1 billion, which is not real close to 30 billion, so we're going to need a different solution. But an int has 32 bits in it. And our booleans don't need to be any bigger than 1 bit wide, which means we can cram 32 booleans into a single int. And that means we can reduce the amount of memory we need by an awful lot. Why, we only need to have, what is it? It's 937.5 million ints. That's doable. But there's another problem. The current algorithm returns a list of all the prime numbers it finds, and we're going to ask it to find 1 billion prime numbers, which means it's going to return a list of 1 billion integers, and Well, that's a lot of memory. Yeah, so the current Java algorithm returns a list of boxed integers, the capital I integers instead of the lowercase I integers. So the boxes, the boxes that hold the integers are like 12 bytes wide. And the integers themselves are 4 bytes, so that adds up to like 16 bytes per integer, and we need to hold a billion integers. So that's like, 16 gigabytes just to hold all the primes. Wait. If the density of primes out by the billionth prime is on the order of 1 in 30, then the billionth prime will be 30 billion. Yeah, that means that the primes will have to be held in long integers, and that means that they're going to take 20 bytes each, and so I'm going to need 20 gigabytes to hold all the primes, and that doesn't account for the overhead of all the list elements. Okay, so clearly we can't just return all the prime numbers we find. What we're going to have to do instead is count the prime numbers we find and then throw them away until we get to the billionth, and then we'll return that one. Oh, yeah, I guess we can do that. But we have another problem. Time. On the board here you see a graph that shows the number of milliseconds required to compute primes up to n. And when I first saw this graph, I was really surprised that this relationship seems to be linear. But after a little thought, I realized that the sieve algorithm's outer loop iterates on the order of n times, and the inner loop, it just gets shorter and shorter and shorter with each iteration. So this should be easy to see if I walk you through the algorithm on the board here. We start with the number line, and if we find an unmarked number, then that number is prime. So then we just mark all the multiples of that number. And of course, right now they're really close together, and there's an awful lot of those multiples, so it takes me a lot of time. But now I go through and I find the next unmarked number. That number must be prime, and so now I mark all the multiples of 3. And as I do that, you can see they're farther apart, right? And so it takes me less time, and there are fewer of them. And then I find the next unmarked number. That number is prime, of course. And so then I have to mark all of the unmarked multiples of 5. In this case, there weren't any. And I go back, and you can see that's getting faster and faster. And now I go to 7, and, well, 7 is prime. And so then I want to get 14, and then I want to get 21, and I haven't even found one unmarked, right? So it gets harder and harder. The inner loop of the algorithm gets faster and faster and faster as we go along. It's those first few primes that have the longest and most difficult inner loop. Now look, I'm no expert on algorithmic science or anything like that, so I could be wrong about this, but it seems to me that if you've got an outer loop of n and an inner loop that gets smaller and smaller and smaller as a function of n, then that's big O of n log n. On the board here you can see a graph of n log n, way the heck out into the millions and billions, and as you can see it's pretty linear out there. And so let's change back to the graph of milliseconds versus n for our algorithm. You see the formula at the top, that's the linear fit formula that was calculated for me by the spreadsheet I was using. And so if we plug 30 billion into that formula, the number of milliseconds that comes out is right around 12 minutes. 12 minutes is not really a very long time for a problem like this, so I'm kind of just tempted to code up our 32-bit hack and run the doggone thing for 12 minutes and get the answer. But I've got this nagging suspicion that we can do better. Yeah, so here's our algorithm so far, and you look at the outer loop, and you can see that it increments from 2 up to n by 1, which means it's going to test every even number. Now, the only even prime is 2, so that's kind of a waste. What we could do instead is after 2, we could increment by 2 so that we were testing only odd numbers. And that ought to cut the outer loop in half. So that reduces the outer loop from 30 billion to about 15 billion. But it has almost no effect at all on the inner loop, which is where all the time is being spent. So I don't imagine this is going to save very much time at all. So is there anything else we can do to speed this algorithm up? Now let's think about that little trick we just tried of incrementing the multiple by 2 instead of by 1. That lays down a pattern in the sieve of every even number other than 2. So that's a nice repeating pattern, right? Even, 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 even. Nice repeating pattern. Now, I wonder if there's a repeating pattern after we mark all the multiples of 3. So here's what the sieve array looks like after marking the multiples of 2 and 3. And as you can see, there is a repeating pattern of marks here that has a period of 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6, of course, is 2 times 3. Now, if we were to mark out the multiples of 5, you would see a repeating pattern with a period of 30. I'm not going to do that on the board, but I think you can work that out. So, since there are these repeating patterns, how can we take advantage of that to speed up this algorithm? Now remember, in order to fit all these Booleans into our memory, we're going to have to squeeze all those Booleans down into individual bits and then cram them into ints, 32 bits per int. Now let's also remember that our hardware architecture probably has a 32-bit bus, maybe even a 64-bit bus, which means that that architecture can move 32-bit ints around in memory pretty doggone fast. Isn't that right, Tweety? Isn't that right? Really fast. So if we can find a repeating pattern of ints, 32 bits that fit into an int, if we can find that repeating pattern, then we can just copy that down the rest of the sieve, and that would be a lot faster than twiddling all those individual bits. Don't even think about it. My God, what an insane idea. Do you have any idea how difficult this is? I have spent a day, I've spent 2 days on this. Oh God, so hard. This is why it's hard. Remember I said, there'd be this nice repeating pattern for the even numbers, but notice that the beginning of the pattern is not part of the pattern. There's a segment at the beginning of the Boolean array that does not fit the pattern, and then the pattern follows. So the repeating pattern starts at 3, right? False, true, false, true, false, true, false, true, like so. Now, when you add the prime number 3 into the pattern, well, then it starts at 4. It actually shifts 1 to the right, and the length of the period is 6. So now you've got an even larger gap here that is not part of the pattern, and then the pattern begins, right? So, and then for the prime number 5, this actually starts at 6. So it always seems to start at the prime plus 1, and then the period is the product of all the primes so far. So, this one has a period of 30. The next one starts at 8 with a period of 210. The next one starts at 12 with a period of 2310. So that's one thing. That's one reason why it's complicated. But then it gets much more complicated because we're storing the Booleans in those 32-bit integers in order to copy integer to integer to integer to integer down the array. You have to find a place where the pattern begins on a 32-bit boundary. And okay, you can do the math for this, and there's some least common multiple thing that you can do to show that, okay, yes. However, it turns out that because of the these prefixes here, it is possible to not be able to start on a 32-bit boundary at all. The pattern simply constantly avoids starting on a 32-bit boundary. So some of these are not going to work. Now, the one that doesn't work most specifically is the number 2, because number 2 is even and every other prime number is odd, and therefore you're going to get this even odd, even odd, even odd, and it's never going to wind up on a 32-bit boundary. The others probably do, but at this point, trying to work it all out and trying to figure out, well, how do you copy them and what do you do and where are the boundaries? And I thought, wait a minute, I've spent a day and a half on this problem, fiddling around and tweaking around and trying this and trying that and discovering that some things can't be done and other things can. And I thought, wait a minute, we're talking about 12 minutes. Never mind. So now, having thrown all that away, all that weirdo optimization, the only thing I've got left is the increment by 2. So let's just see what the code looks like. It's pretty simple. So here's everything here. Here's the sieve algorithm, right? It's all in Java still because we're doing things fast. And the sieve is going to return a list of longs now, not ints anymore, longs. And okay, we're going to create a list of longs. I'm not going to use this, right? You can see down here I've disabled the add. It's old code. I left it in because when I want to get smaller primes, I just stick that back in. The ints, on the other hand, the sieve array itself is a number of ints, which is n divided by 32, because we're cramming 32 bits into each integer, right? So we can shrink the size of the array by a factor of 32. So we create that array this way, fine. We also have a variable here that we're going to use to count how many primes we've created, and with that we're going to print the billionth prime. The rest of this is pretty straightforward. Here's the normal old sieve loop here, except that I put this cute little thing in here to increment the candidate by 2 once you get past the first 2. So that's that, doubling of the speed of the outer loop, even though it has no effect at all on the inner loop, right? So whatever. And then, of course, if it's not a composite, then it must be prime. And this is where we say, okay, count it. And if that count is greater than or equal to 999999999, then start printing. And we're going to print the prime and the count of the prime so that we know what the billionth is. And then once it gets up to 1,000 or 1,000,001, we'll stop printing it. So that should print like 3 primes. And that will let us know that they're close together, because I don't want to worry about whether or not the primes are wrong or anything like that. So, I want to make sure they're fairly close together. They should be like, within 30. And then we do the final multiple loop of the sieve, and that's just normal. No special. You wouldn't believe the code that I had in here to try and do that replicate the pattern down the array nonsense. And I ripped it all out. Now it's one line set composite. Okay, so the trickiness here now goes into just this bit twiddling. And then this is not rocket science stuff. If you want to set the composite, if you want to say that this number is a composite, you want to set that bit in the sieve, then you work out what word it is by dividing by 32, and you work out what bit it is by getting the remainder of 32, and then you shift it a 1. You shift a 1 left by that remainder, and then you just OR it into the word. So that's pretty straightforward. And if you want to ask the question whether or not something is composite, well, you do the exact same math to figure out the word and the bit and so on. And you shift the bit exactly the same way. And then you AND with that bit. And if the result is non-zero, then you've got a composite. And that's really it. That's the whole thing. Nothing much more. Same old algorithm as before with those few changes. And so the results are in. The billionth prime is 22 billion 801,763,513. And I printed some primes around it, and you can see that those primes are nestled fairly close with a distance of about 12 and 24 and 14. So that makes pretty good sense. It appears that the density of primes out at the billionth prime is really not much greater than about 1 in 22 or 23 or something like that. So we didn't really have to go all the way out to 30 billion, but who knew, right? So, okay, we went a little farther than we had to, but it's okay. It's okay. We got the billionth prime. Now, I know I said I was just going to print 3 prime numbers, but here on the screen you see 4 prime numbers, which just goes to show you that there are really only 2 difficult problems in computer science: cache invalidation, naming things, and off by 1 problems. Are these numbers really prime? Well, we've got a little algorithm that will tell us that. It's our old prime factor algorithm, way back from episode 3. So let's see. Factors of, let's try this number. Yep, that looks like it's prime. Yep, let's try this one. That one looks prime too. That's the billionth prime, so must be prime. That's good. And let's try this one. Yeah, that one looks prime. Yep, okay. And the last one, I think they're all going to be prime, aren't they? Yep, okay. They all seem to be prime. And just to show you, let me reduce this by 1. I'll turn that into a 6, and we'll get the prime factors of that particular number. God knows what they are. Oh, yeah, 2, 3, and some gigantic number. Okay, good. Notice how fast that algorithm is, even for large numbers, and that's, of course, because we're only going up to the square root, and never mind, you know all that. Okay, so how much time did this take? How much time did we save, right? Our initial estimate for how long this was going to take was going to be on the order of 12 minutes. And after measuring how long it took us 682 seconds, which is roughly 11 and a half minutes. So, did my optimization save any time at all? Maybe 15 seconds or so, or maybe a little bit more. I mean, we did add all that bit manipulation, the bit shifting and stuff to cram the bits into 32-bit integers. So, that probably took a little extra time. So, maybe we saved a minute, or maybe 2. Or maybe not, because, you see, blind optimization is almost always a fool's errand. What's blind optimization, you ask? Blind optimization is optimizing things without knowing where the time is actually being spent. I feel a story coming on. So this goes back probably to the late 1980s. A good friend of mine, Jim Newkirk, who was also my business partner at the time, and I, and several other people, were engaged on a project which involved a lot of really intensive computational geometry. I wrote a little algorithm to search a list. And in the beginning, I just used a straight linear list search because, why wouldn't you? Why do anything more elaborate than that? So Jim comes to me at some point and he says, this algorithm is taking a really long time. We're doing an awful lot of these list searches. Maybe we can speed this up somehow. So I look at the list search and I think, well, I can obviously turn it into a binary search, and that would improve it by massive amounts because the number of things we were searching was on the order of hundreds or thousands. And so, okay, yeah, you can speed it up like crazy with a binary search. So I wrote that up. I wrote the binary search up. Took me a long time, test. Binary searches are not easy to write in C. This was all done in C++, and we were using the the Rogue Wave reusable library, which was very common at the time, right? So anyway, I wrote this all up and I got it working in C++, binary search. It was great. Gave it back to Jim, and Jim said thanks very much, and he went off to work. And he came back about a day later and said, it's not any faster. And I said, well, that's impossible, because this was a linear list search and now it's a binary search. And he shook his head and said, it's not any faster. And Jim went away and he did a profile of what was really going on. And then he came back to me a few hours later and he says, yeah, the linear search, the binary search doesn't matter at all, because the real problem was that we were adding components to a Rogue Wave list, and every time we did that, it had to copy the list to a new list. So there was this terrible copying problem, which he was able to solve by pre-allocating the list size. So let that be a lesson to you, and to me. Blind optimization is a fool's errand almost every time. Before you optimize something, measure. Measure first. Figure out where the time is really going. If you just start to optimize here and there because you think that's where the time is going, you're almost certainly going to be wrong. Anyway, that's the episode. I hope you enjoyed yourself. I hope you learned something. I hope you appreciate the fact that we just did something 30 billion times. Yeah, I know. Okay, boomer, right? Anyway, you're not going to want to miss the next exciting episode of the Euler Project, episode 8. Long products in a series.